Okay, this is, today I'm going to talk about the injective coloring. It's a kind of a coloring, and it's joint work with my friend. Actually, Dan and Geshin both are they're the student at the University of Illinois at Urbana-Champaign. So now after they graduate, so they moved on another place. So Geshin is now is permanent position, and then he's looking for permanent position this year. But as you know, the economy is terrible in USA. So he has some stress now. So injective coloring, okay, okay, so what is the injective K coloring is, so we give a color on vertex such that if two vertex U and V have a common neighbor, then we give a different color. And then as usual, injective chromatic number is the least number of color to have injective K coloring. So this concept was introduced in 2002 by these 4 people. Maybe I cannot pronounce the second person, so I want to skip the pronouncing the name. Can you pronounce the second person? Krach. Always I think that he's maybe Czech or you Czech, yes. Always their name is very difficult to pronounce. So, okay, so here we have a simple example. Okay, if you have this subgraph, then A1, A2, they have a common neighbor W, so they must have a different color. So also A1, A2, A3, they should have a different color. Anyway, all labeled of W must have a different color. But here, this is not, it doesn't have to be proper coloring. The reason is A1 and AW, they might have the same color. Okay, this is only difference from the regular coloring. And then, so here you have C5, then we can give this coloring. So this is acceptable, this is injective coloring using 3 colors. So here, from the first example, you can see the lower bound of injective coloring chromatic number is at least maximum degree. Yeah. Okay, so far good. So I think I should move very slowly in the beginning part, right? So if you have any question at any time, please ask me. So trivial bound. So lower bound is the maximum degree, as you can see the first example. And the upper bound is just simply number of second neighbors. And then, what is this? And then in 2002, these 4 people show that upper bound, it doesn't, we can reduce the upper bound by delta, right? Delta minus 1 actually. And then this upper bound can be achieved by very special graph that is using projective plane. Of course, the lower bound is achieved. So from this point of view, it seems it is solved already. Lower bound, upper bound are achieved, so it's not interesting anymore, right? So it's bad, actually, in some sense. So how can you achieve the upper bound? Okay, lower bound we can achieve by a D-regular graph, some special type of D-regular graph. And then to get upper bound, okay, so story is we have a projectable plane, so simply okay, planar plane okay, we have a planar plane, then we construct a bipartite graph from using point set and line set of lines. So here, if we have a line 1, 2, 4, and then maybe 1, 3, 7, then maybe
2, 6, 7.
maybe yeah, range is so and up above in the top part. Then 1 to 4, then we connect this way, and 1, 3, 7, we connect this way, and 4, 5, 7. So if you construct the graph this way, then this is 3 regular. And then, every 2 vertex in the path. So and every 2 line must have intersection. That means if you have any 2 vertex here, they have common neighbor. So this means this must have all this. They must have a different color here, right? So how many points are, how many vertices are here? Is 7, right? So actually this explanation is the general of this pattern. Okay, is so far good? So we can skip all of this. And then for simple, very special type of graph, okay, the even cycle whose length is divisible by 4. Then we can show this injective chromatic number is 2, and different and other cycle is injective chromatic number is 3, and for 3 is injective chromatic number is delta. And then interesting point is we don't know exact answer for the hypercube. The hypercube is very special type, very simple type of graph, but still we don't know. So this is just the general upper bound for any n. So if you reduce this bound, reduce a little more, then it will be very interesting. And then for some special n like this, then its injective chromatic number is n. I think this you got this result from using coding theory. This case corresponds to perfect code situation.
So that's if and only if?
Yes.
So n is the lower bound, right?
N is lower bound. Yeah. Any other question? And then so let me introduce some related problem with this. So there's a square of graph. So what is the square of graph? It has the same vertex set, and then 2 vertex are adjacent if their distance in G is at most 2. So this graph can become everything is adjacent. Also, if we have this way, this one, then new graph is so white color is the C6 is the original graph, and then this and with the yellow color, this one together, this is become the square of graph. So now I hope everything the definition of a square of graph is clear. I hope, and then here, if two vertices have a common neighbor, then we make them adjacent. So we define the graph this one. Then this we call this type of graph. Some people call neighbor graph. Neighbor actually, I need to delete ing. The neighbor graph. Actually, so injective chromatin number is actually is same as the chromatin number of a neighbor graph. So general lower bound and upper bound is as follows. So again, every neighbor must have different color in the square of graph, including this center. So delta plus 1 is trivial lower bound because it's at least the clean number is at least this much. And then also enlarged this way, because delta squared is number of second neighbor. I think my first slide was something mistake, but yeah. Okay, let me give you a little more hint. So sometimes it becomes very complicated. Okay, we have 7 vertices. And then here, chromatin number of this square graph, what is this? Every 2 vertices are within 2, the distance between every 2 vertices are within 2. So it's 7. So this type of problem was started by Wegener in 1977, and then he he announced this conjecture, and then unfortunately this conjecture is still open, but in some sense it's very good to us because we have something to do. And then but for this conjecture is wide open except the first one, when delta is 3. So it is proved by very famous graph theorist Carsten Thomassen. And actually, but I couldn't see his paper yet. The reason is maybe only Leffery can see his paper yet now. So maybe in 2001 or 2002, he said, okay, I solved this, but so far nobody was able to see his paper. So later it was found, it turned out, he claimed, okay, I solved this, but he found some mistake in his paper. So he withdrew the paper and then correct and resubmit. So that's why nobody can see his paper yet. And then the best result for this type of problem for general delta, so actually the conjecture was this, and then you can see the huge gap between 3 delta over 2 and 5 delta over 3. In something not huge gap, but something gap. And then if you want to remove this constant part, then we have to pay something. That is, our delta must be very big. And then this graph is planar graph. So in some sense, I mean the planar graph with the maximum degree 241 is very special graph. It's not general case, right? But unfortunately, this paper is involved with very complicated discharging techniques. So, I mean, I hate to read this paper. And then recently, statistically, by using probability, these famous four people show that, okay, the conjecture is true for large size of graph. Then let's come back to injective coloring. So we can see, we don't know what is the interesting problem, and we can consider the first problem, and then unfortunately was good. So after I come here with Dr. and I solved this. So it's not conjecture yet. It's not conjecture. It's not conjecture anymore. Just fact. The second one is still conjecture. So it's open to everyone. Second conjecture is very similar to this one, right? And then for second conjecture, I want to pronounce it as Rashford, but he wanna call it by Hushford. He's French, and his pronunciation says he said Hushford. Then Han and Hushford Wang prove the conjecture when the G is K4 minor free. What is the K4 minor free? Yes, if you have any question, then ask Dr. Wang. He's expert in that area. Don't ask him about what is K4 minor. But when delta is 3, it's in some sense very simplest case, but still open. But it seems it's most difficult case, I think, because there's very tiny room to improvement. And then recently, again by Czech people, okay, so planar graph, so we consider Gauss. So Gauss is the smallest size of a cycle of the planar graph. And if Gauss is Gauss is at least 5, then injective chromatin number is at most delta plus 4. And if Gauss is at least 10, then injective chromatin number is delta plus 1. Then what's the meaning of a third result? So can you figure out what is the meaning of a third result? Actually, well, let's say this. The Kling number, well, I don't know how to, if I can say Kling number. Kling number of it's not Kling number, but injective chromatin number, the lower bound of injective chromatin number is delta. So the meaning is, if Gauss is at least 19, then its injective chromatin number is as small as possible. So also in terms of maximum average degree, so maximum average degree is given by the function. So we divide number of edge by number of vertex. So simply,
So you don't multiply.
Oh, I need to
by 2.
Yeah, I need to multiply by 2. The reason is the top part, it is exactly sum of degree, and then so sum of degree, we divide the sum of degree by number of vertex. That's average degree. So now you see this type of graph. Also, you can see this type of graph, which looks more complicated. This one, right? And this one has a small average degree, right? The complete graph should, if average degree is high, then it has complicated structure. So naturally, if average degree is low, then we don't need many colors. So we can give a coloring with a small number of colors. So maybe you are not interested in this number, right? Because so many lines, and then it's not clear what's the meaning of this number. But so you have some list of results, and then you can see the upper bound, as upper bound is decreased, the average degree is also decreased. So why are we interested in average degree? So typically when you say, okay, we are not say, okay, if Gauss is at least 6, then its injective chromatin number is m-most delta plus 4. So in this case, how can you prove this? How can you show this? Maybe you have two type of direction. For typical type of direction is, first we calculate maximum average degree, and then convert into Gauss condition. Then how can you convert Gauss condition? That is, we use this formula. So this is why the maximum average degree is important. For instance, here, so when you, okay, if maximum average degree is 3, then just plug in 3 in, no. Yeah, Gauss. Then what is the smallest Gauss to become maximum average degree m-most 3? That is 6. So if you plug in 6 here, then you get 3. So maybe even though if you are not familiar with the maximum average degree, then but it's very important parameter. So another important advantage of maximum average degree is, okay, when you say Gauss, it's always planar graph. But sometimes we can say Gauss for general graph. But typically when you say Gauss condition, then it's for planar graph. But if we have result in terms of maximum average degree, then it doesn't have to be planar graph. So it means we have a general result. So okay. So question. So our main question is, what is the maximum average degree to guarantee injective chromatin number is m-most delta, and also m-most delta plus 1 and m-most delta plus 2. So our result is as follows. Its maximum average degree is 5 over 2, then its injective chromatin number is m-most delta plus 1. And then if maximum average degree is less than 42 over 19, then injective chromatin number is delta. Okay, this is purely in terms of maximum average degree. So now, let's restrict more. Okay, we just focus on Gauss condition. Then we have this type of result. If Gauss is at least 9, then upper bound is delta plus 1. If Gauss is at least 13, then is injective chromatin number is delta. So now compare these two results. So once we show that if maximum average degree is at most 5 over 2, then we can say, okay, if Gauss is at least 10, then upper bound is delta plus 1. So how can you get the number? So it's just plug in Gauss 10 here, then it's 5 over 2. And then if maximum average degree result is like this, then we can say, okay, Gauss is at least 21. But if just focus on Gauss, then we can reduce from 10 to 9. And also we can reduce a little more from 21 to 13. But we have some small restriction, but it may not be small. It's big restriction. I mean, in this case, the delta is at least 4. And then our second result, second stage of result, okay, is actually delta is at least 4. Then if maximum average degree is 14 over less than 14 over 5, then its upper bound is delta plus 2. And then if delta is 3, then we have this result, and then this result is actually sharp. The reason is we have a construction that maximum average degree is exactly 36 over 13, but its injectable chromatin number is 6. How can you get this construction? Again, using Panaplane. You remember the bipartite, and then when you construct, we change a little bit, then we can get the construction. And then I think it's this number could be headache to you. Okay, this is previous result by Czech people. And then, okay, they show that, okay, if Gauss is at least 10, then its upper bound delta plus 1. Then our result say, okay, if maximum average degree is 5 over 2, then its upper bound is same. What's the meaning? Our result imply, okay, the same as Gauss is at least 10, its upper bound is delta plus 1. But it has one advantage. What is that? Here, they require is the graph is planar, but our result, it doesn't have to be planar. It's general graph. So we generalize the result. And the second case, we show that, okay, to become the upper bound is 5, then we have tight condition for maximum average degree. And then another interpretation of our result is, in the previous paper, these three people show that, okay, if maximum average degree condition is like this, then the upper bound of injective chromatin number is delta plus 3. So our question is, okay, if you have the same condition, then can you reduce this upper bound? Then we try to reduce the upper bound. Then finally, it turned out we cannot reduce the upper bound in generally because of delta 3. But we can reduce upper bound when delta is at least 4. This is the meaning of our result. The schedule proof is, so always at this time we have some headache, right? So actually, so my advisor is Doug West also, but also I learned a lot of mathematics from Professor Alexander Kostachka. He's from Russia, and then so they have two different opinions. So Doug West, when I was a student, so they trained me how to present at a conference or seminar. So Doug West always ask, you must present proof. But Kostachka said, no, you should not give proof. So once you give proof, then immediately audience gets sleep. So actually I follow the Kostachka's opinion. For this seminar, so it is 50-minute talk, so I include a little bit of proof. But so if you feel sleepy, then it's okay. So even though you get sleep, then I forgive you. So always okay. So let me explain very brief sketch of one case. Okay, if maximum average degree is 5/2, then its upper bound is delta plus 1. So, and for special case, when delta is 3, then our typical style is like this. Always we start with minimal counterexample. Here minimal means every proper subgraph satisfies the condition, but that graph does not satisfy. I mean, if the theorem is not true, then there's some bad example, bad graph, right? So among the bad example, we select minimal, but it's not minimum, so minimal. And then reducible configuration, it means this subgraph cannot appear in the minimal counterexample. It means once this type of subgraph appear in the minimal counterexample, then we can say this is not counterexample. So degree of vertex 1, we can have this type of subgraph. Also, two consecutive D2 vertex. We cannot have this type of subgraph.
Why? You can probably explain.
Yes. So once we have this graph, then we delete this middle part. Then this have how much? The new graph have injective 4 coloring, because this is a minimal counterexample. This graph have smaller than this, right? So now we want to extend from the given proper coloring to here. Then let's think our list. Now, how many colors are forbidden here? 1, 2, 3. So we have at least one available choice. Also this at least one available choice. So they are adjacent, so we can give color arbitrarily. So through this, given proper coloring, we can extend the proper coloring whole graph. That means this graph is not counterexample, so it's contradiction.
So what happens if U and V are same vertex? I mean, if they form, if U and V are same, then those two vertices in the middle should have a different color.
So you wanna say this one?
Yeah, but
Still the forbidden list is just 1, right? Available list is 3. Yeah.
No, forbidden is 2.
2, 1, only with this.
The one at the
No.
yeah, that
No. Oh, 2. Okay. So now we construct some new graph, that is, we call it G23 graph. Why? We just focus on degree 2 vertex and degree 3 vertex. So here, so if degree 3 vertex are adjacent like this, then we just remove the edge. So this graph becomes this way. So then how can you use this? Then so we have some complicated statement. So here, so main point is if G23 graph does not has at most one cycle. So what happens if graph has at most one cycle? If graph has no cycle, at most one cycle, then number of edge is at most number of vertex. So we use that observation. So here, what the number of edge correspond? That is degree 2 vertex, and the number of vertexes correspond degree 3 vertex. So we use that observation, and then so once each component does not has at most one cycle, then we can say, okay, that's maximum average degree is at least this way. So we forget, and then other case is, okay, what if component has degree 3 vertex? If you have at least 2 cycle, if component has at least 2 cycle, then it has degree 3 vertex. Is it true? Yeah. Then here you can see temporarily, if you forget this is degree 2 vertex, then the edge corresponds actually degree 2 vertex. So we use the observation. Then, so we are almost the final stage. We have only 4 slides are remaining. So you should be happy in a moment. So once we have this one, then we use, actually more than 4 slides. So we use Aldous-Rubin-Taylor theorem, and so we use some known result about the list coloring. So I'm gonna skip this part. So if you're familiar with the graph, then you can recognize this result, right? So now, our main procedure is like this. Okay, U has a degree 3 vertex. Once we have this structure, then we delete this part, and then proper coloring has coloring, injective delta plus 1 coloring. And then using delta plus 1 coloring, we extend to vertex here. So can we extend our coloring to the vertex cell over there? Yes. So the reason is if you consider neighbor graph, then yes, it has two components. One component is, okay, just think the, how can you say, this is dark vertex, right? Then they are connected. We have two components. So one component is like this. And then here, U is the degree 3. Wait a minute. In my slide, the Y means U. Oh, okay, right. U has 3 neighbors, but it has list 4. Because it doesn't, no. Suddenly it's very confusing.
So you assume that some other components are pre-colored.
Yeah, right.
And so therefore and this component is not yet colored at all.
Right.
So 4 colors are still remaining.
But this is colored.
Oh, is it? It's in the same component.
Yeah. Suddenly it looks 3. What happened?
No, that's not.
It's not colored.
Yeah, it's not colored.
Oh, yeah. You should have more. It's not colored, is good. Okay. Then it has 3 neighbors, but 4, the list size is 4. This vertex is not colored. So it's okay. And the second case is we consider this component. And then, so Aldous-Rubin-Taylor, the theorem says if graph is degree choosable, if every block is not only, if and only if every block is complete graph or odd cycle. But this is this red graph is too connected. It's block, actually block, but it's not odd cycle nor complete graph. So we can give color from given list here. So we can extend color this way, and then we have 2 challenging problem. And then really end. So we are happy now.